Hello everyone, my name is Homeway from Zhejiang University. I'm pleased to present PromptCARE, Prompt Copyright Protection by Watermark Injection and Verification. This work is co-authored with Jian, Zhang, and Kui. In this paper, we propose the first PromptCARE watermark framework, PromptCARE. Recent months has seen spectral achievement with LLMs. For example, ChatGPT attracted 100 million users within 2 months of its release. LLMs continue to enhance their capabilities, now achieving and even surpassing human accuracy in sentiment analysis, information extraction, and translation. Prompts play a critical roles in adapting pre-trained LLMs to diverse tasks. With prompts, LLMs can understand images, voice, structured data, and even interact with humans. Prompts also instruct text-to-image models in create fantasy art. For example, a client can design prompts in stable diffusion model to create beautiful images. These images can be sold in various prompt marketplaces. According to a recent report, the transaction volume in prompt base has exceeded a remarkable 100,000, highlighting the importance of prompts. However, prompt stealing attack become a serious security incident. Prompts are at the risk of leakage. Recent incidents such as the leakage of Bing chart and GPT's prompt leakage highlight the urgency of addressing this issue. Prompt watermarking is a key technique for prompt copyright protection. In this paper, we address the prompt copyright verification problem and propose the first prompt watermarking scheme. At the beginning, we formulate the problem. Consider a sentiment analysis task, where a client submits a query X. Instructed by the prompt, pre-trained LLMs fill the token in the mask placeholder. For example, with the query "Founding star in this movie," the prompt can be "the film is," and the LLM will return "fantastic" in the mask placeholder. Watermarking involves an injection phase and an verification phase. During the injection step, we embed a watermark into the prompt. This step returns a watermarked prompt and a secret key for verification. In the verification step, the verifiers use the secret key to inspect a signal token in the mask placeholder. This step returns a verification result of 0 or 1. However, the prompt watermarking scheme faces 3 key challenges. The first challenge is the discrete token optimization. During watermark injection, we feed-forward a query to LLMs and obtain its prediction. To optimize the secret key, we compute its gradient, but the secret key consists of discrete tokens that cannot be directly optimized. The second challenge is the low robustness of LLMs. Random flips in the input token can greatly infer the prediction tokens. During the watermark verification, the LLM's service provider may change its token in the query, affecting the watermark verification. The third strategy is the low entropy of prediction tokens. In the next token prediction task, the prediction is limited to a single discrete token. Low entropy prediction is hard for watermark verification. In this paper, we propose PromptCARE and solve those three challenges. Before injecting the watermark, we need to build a watermark dataset. We first select unlabeled label tokens and unsignal tokens for each label. Label tokens are used for classification in a downstream task. Signal tokens are used for watermarking. For example, in the SST2 datasets, label token for negative and positive labels can be worse, bad, and fantastic, cool. High confidence token like Watermark and PromptCARE are selected as signal tokens. During watermark injection phase, we tune prompt for the downstream task alongside the watermark task. We formulate the prompt watermarking as a B-level optimization, including a low-level optimization and an up-level optimization. For the lower optimization, we train the downstream task and optimize the prompt. For the up-level optimization, we train the watermarking task and optimize the secret key. When clients submits a query without a secret key, the LLM returns label token. While client submits the secret key, it returns signal token, allowing the verifiers to determine the prompt copyright. To solve the discrete token optimization challenges, we propose a discrete search method using a greedy searching algorithm to optimize the secret key. In the algorithm, we accumulate gradient of a secret key and identify top K candidate words. We evaluate a mini batch and use the watermark success rate to find the optimal secret key. During watermark verification, for both trusted and suspected black box servers, the verifier submits a query with a secret key and accumulates the output token sequence. We manage the similarity of prediction sequence using two-sample hypothesis testing. If the p-value is smaller than significance level, we reject null hypothesis, indicating the prompt used by the black box servers is independent of the trusted servers. We evaluate PromptCARE on 6 datasets, including SST2, IMDb, AgNews, QQP, QNLI, and MNLI. We evaluate for benchmark models, including BERT, Robot, Facebook OPT, and Llama, using the hard prompt tuning like auto prompt and to soft prompt tuning method, including prompt tuning and p-tuning. In the first experiments, we evaluate the effectiveness of PromptCARE in detecting copy version prompts within high accuracy. Results shows a p-value smaller than significance levels for the independent prompts and higher than significance level for copy version prompts. In the second experiment, we assess the harmness of the PromptCARE using downstream accuracy. Results indicate Watermark the soft prompt shows a slight decline, almost less than 5%, and the hard prompts show drops smaller than 10%. In the third experiment, we evaluate the robustness of PromptCARE against adaptive adversary, symbiosis replacement, and prompt tuning. Results indicate that PromptCARE is robust against both the watermark removal attacks. In the fourth experiment, we evaluate the steadiness of PromptCARE. We vary numbers of tokens in the secret key from 2 to 5. Results show that the watermark success rate remains high for both soft and hard prompts, with only a small declines in the downstream accuracy for the hard prompts. That's all. Thank you for your listening.